So welcome back, everybody. On stage with us, we have James Powell, who came all the way from America. He is board chair at NumFOCUS, and he's going to present to us a talk that didn't have a title yet, but it's titled Cumulative Index Max. So a round of applause for James, please.
Hello, everybody. This is Cumulative Index Max. We're at PyData Amsterdam. It is September 15th, 2023. My name is James Powell. You can follow me on whatever platforms are still around to follow people on. I'm basically James Powell, or don't use this code on all of those platforms. For those of you who have seen some of the talks that I've given on YouTube, you may have seen earlier this year at PyData London, I gave a talk on grouped weighted summary statistics in pandas, which turns out to be a very useful but difficult problem to solve. In that talk, I had discovered something extraordinary. I had discovered the 4 words, when put into a talk title, constitute the most boring talk title ever created: grouped weighted summary statistics. But I have something exciting for you today. I have found an even more boring talk title, and only 3 words: cumulative index maximums. So, in this talk, what I want to share with you is some of the thought process that arose when thinking through the problem that was discussed in group-weighted summary statistics. Specifically, cases where pandas is simply not fast enough or simply does not implement the mechanisms necessary to solve useful problems, and what you do in response. Additionally, how we can think about optimizing code, especially where we have to optimize code by working around deficiencies, limitations, or missing features of tools that we use. So let's take a look. Now, I want to set up the problem for you. And so for cumulative index max, the problem setup is actually fairly straightforward. Let's assume that we have a data frame, and in that data frame, we have dates, we have tickers, and we have prices. Very, very common data set used in many sort of financial analyses. Here you can see the data is randomly generated, and for the most part, we don't really care exactly what the data is, other than that it constitutes some random walk over 180 days with 100 different names. If we have this data set, and we think about the analyses we might do on that data set, it stands to reason that one of the more common analyses we might do is to figure out what is the minimum price, what's the maximum price. Very common analysis that may come up. Similarly, what is the day where the minimum or the maximum price occurred? Also a very common analysis. We want to know when we hit those extents. Although you can see, unfortunately, in pandas, it doesn't really know how to deal with that multi-index properly, and so as a consequence, we get something a little bit noisy. We get the day and the ticker, but the ticker is repeated. So we end up needing to do this a little bit more clumsily in pandas to get the result we want. Unfortunately, the new group keys argument that's provided to us in group by doesn't actually remove the extra group layering. In this case, it would, for example, remove the extra superfluous group key layering when we do, say, a .apply operation. But here what we have to do is we actually have to break this down into a user-defined function passed to ACK. And so here we have something very useful. On the 15th of January, one of these tickers saw its minimum price. On the 8th of April, it saw its maximum price. Similarly, we might want to do a cumulative minimum and a cumulative maximum. As we go through the data set, we want to figure out, okay, given this cumulative minimum and cumulative maximum, what is the highest price we've seen so far? What's the lowest price we've seen so far? It can give us some information about, say, the extents of where this pricing might arise. And given that data, we could do something interesting, like we could say, subtract it from the series and figure out how far away we are from our minimum or maximum. Except, one of the unfortunate things about pandas is, it is very easy to use pandas without really knowing what we're doing and really knowing how index alignment works. And when we do that, we end up with these horrible tracebacks with error messages we can't make heads or tails of, cannot join with no overlapping index names. Well, unfortunately, I've tried to do an index alignments between a data frame and a series, and I've forgotten that when we index align a data frame against a series, it aligns the index of the series against the columns of the data frame. So the solution here is quite simple. I just have to create a secondary data frame that index aligns properly, where the column names of that secondary data frame are the column names of the first data frame. And now I have something fairly useful. This is the distance from the minimum or the maximum price for every day in my data set. And you can think of this very similarly to if I want to do some kind of expanding z-score, or if I want to do some kind of normalization. How many standard deviations am I away from the maximum that I've seen so far will be a very useful analysis. The thing is, when I take this data set and I think about those kind of operations, these cumulative mins and these minimums actually come up quite often. Even an index min operation may come up quite often. For example, it may be the case that I don't want to just find what the price was when it was lowest. I want to find what day that occurred on. And when we think about pandas, we often think about pandas in terms of this index as the core coherent metaphor. It's the mechanism which defines the semantics of almost every operation in pandas. And we can think largely that when we talk about a pandas data frame, we're not talking about a two-dimensional structure, we're talking about a one-dimensional structure, some collection of entities where those entities have aspects that have been represented in their columns. It's a very classical struct of arrays, array of structs type of transformation. And as a consequence, on an arbitrary data frame, we may do minimum and maximum operations or cumulative minimum and maximum operations. We could express those in terms of expanding minimum and maximum operations, although we get the exact same result, just as, for example, a fold over add is the same thing as a sum operation, or a fold over min is the same thing as just a min operation. It's often the case that we want to do an index min or an index max. And the reason we want to do that is to do some sort of lateral query. For example, we want to know for this data set, what are the values of A where we see the lowest value of B. We want to do some sort of lateral analysis. And this is why we would use the index min or the index max, because we'd say that the index is what's tying together these disparate data sets, or what's tying together these different columns of these data sets. So we'd first do an index max on B, and then do a lookup on A. It's a very common way that we do these lateral analyses. Historically, as you know, pandas did not have the key function protocol implemented, like the max, the min, and the sorted in pure Python, which is how we'd solve these problems in pure Python. Instead, we have to go through this subordinate structure through this index in order to solve the problem. Similarly, it's not too uncommon for us to do some very complex things with this sort of index construction. For example, this analysis here, albeit very clumsy and with a lot going on, is just finding what are the values of B, where B is around 1 standard deviation. I should actually fix a small typo in here. The values where B is around 1 standard deviation of its min, and A is around 1 standard deviation from its max. And we do that by figure out where A meets this criteria, give me the index, and do an index level intersection, and then finally at the very end, actually look up the data. This is why, for example, for those of you who have followed me on any platforms, you may have heard me threaten that the next version of pandas, or the tool that replaces pandas, might be a tool that is just indices only, because ultimately a lot of the analyses are really just happening on the index, and the data, surprisingly enough, is quite secondary. In fact, in truth, in many cases, I don't care about the data, I care much more about the indices. But that might be a little bit too controversial for all of you. Unfortunately, what is missing in pandas is a cumulative index min or a cumulative index max. This is simply and completely missing. And it is an incredibly useful thing to solve very real problems. You have cumulative min, you have index min, but you don't have the combination of the two. And the reason for that is something which you can imagine there might be some debate over what the API for that might look like. As we'll see, there are some variations on how we might model that. But for the most part, the truth of the matter is, many of the tools that we use, such as pandas, are tools that are under active development. They are tools that are not complete and in maintenance mode, but they are tools that are constantly adding new features. And we still risk to this day that something that we need to do is not yet implemented, and we have to figure out what do we do in the interim of time between when we discover we have this problem and when the pandas core developers have the time to go and solve that, assuming, of course, that we ourselves are not willing to put the effort into fixing pandas. Now, I will say, when I discovered that we were missing this, I went into the pandas source code and tried to see how much work it would be to add in a cumulative index min and a cumulative index max, because I thought, if index min and index max already exist, isn't it just a cut and paste job? Unfortunately, that's not the case. It is also that libraries like pandas are very complex, and they have many layers of indirection, and it does take a while for you to become familiar with how you can slot in these new methods. It is not an easy feat to add some new functionality to pandas for a library of its level of maturity. So, facing that, I wonder, how do I go about solving this problem? And again, really all we're looking for are analyses where we have some entities and we're trying to figure out some sort of lateral query of the entity. Where in pure Python, we would do this with just max and a key function, but we're stuck at the Python speed. Or we'd even do these kind of analyses with some kind of comprehensions. But you can see the comprehension syntax is very clumsy here. There's a lot that's missing when we don't have the ability to quickly just access columns of this data. Pandas is more than just a convenience level on top of NumPy and D-arrays. It adds some very meaningful APIs for accessing aspects of the data in a fashion that's much less clumsy and much more fluent than what you can do in pure Python, and whereby that API allows you to encode the operations you want to do within a restricted computation domain. In other words, you can do them not at Python speed, but at C speed, at the speed of whatever Pandas is built on top of. And so, with that said, in the absence of, in this case, a group by cumulative index min or cumulative index max, we have to figure out how we want to structure this ourselves. And naturally, just as index min and index max are just an expanding min or expanding max, we might think we could start with the expanding operation and then get in the index min or index max. Unfortunately, there is no index min or index max attached to expanding. Otherwise, this problem would already be solved. And unfortunately, as many of you know, the expanding API recently became much more restrictive. Historically, the expanding API would allow us to do pretty much anything we wanted to within a user-defined function. So, for example, we could write a user-defined function, and in this user-defined function, we could just do index min and call it a day. Except the expanding API these days requires that all of the operations done in a user-defined function are done only on numeric columns. And you can think, why is that? Well, this is very meaningful for us if we think about what makes Pandas code fast and what makes Pandas code slow. What makes Pandas code fast are cases where we can, with some generality, drop down to the lower level. We can tell the Pandas API to do something, and then it figures out how to encode that in operations at these lower level structures, whether NumPy level structures or arrow level structures. And in the case of an expanding, you can think you lose extreme generality in order to be able to say, okay, I have some operation, I want to perform it on every single subset of this data. Fundamentally, any UDF that you perform on an expanding data structure is going to be performed row-wise, because you have to perform it on 1 row, then 2 rows, then 3 rows, and 4 rows. Therefore, the expanding API fundamentally is going to operate at Python speed. So what's the point of it in the first place? If you're already at Python speed, you might as well just write a Python loop, which I think gives a reasonable justification for why they limited the scope of the expanding API. The Pandas core developers probably assessed that, you know what, we're at Python speed anyway. If we allow people to do anything they want, you don't need a special API to just write a Python for loop. And so the answer for this question may be, what if we just write a simple Python for loop and do things that we are told we are not supposed to do in Pandas? We are not supposed to iter rows. We are not supposed to do it .items. We are not supposed to operate row by row. Question is, how bad could it really be if we do that? And so a Python implementation of cumulative index max, fairly straightforward. We create a return value that's indexed similarly to whatever we passed. We write a for loop operating over the .items for a series that's the equivalent of the .iter rows. And this code here is about the dumbest code for figuring out a max that you ever saw. This is your computer science 101 version of a max, which, by the way, is a good thing. Because, as we'll see, when we have to work around the deficiencies of some of these projects or the gaps in these projects, I think that it's generally a good case where the workaround that we have is written in the dumbest possible code that we can write. In part because we understand that the temporality, the transientness of our workaround, it's not going to be around forever. The Pandas developers will eventually solve this problem, and we really don't want to put a lot of effort into writing, maintaining, understanding, validating the code. And so that I can write this in a couple of lines of very, very stupid code is actually a very good thing. And I can do that, and I can time it, and it takes me about a half a second to operate on this data. And you can see I can even do the subtraction from the original data set, so I can answer a question of how many days since the last time you saw a high price. This cumulative index max problem on this data set is enormously valuable. This answers the question of how many days since you were last at your maximum price, which you can imagine, if you've watched even a small amount of CNBC, is an easy way for the people on CNBC to fill time with nothing of actual knowledge or interest or value to say, oh, this is the last time that we've seen this price in 32.4 days. Well, now I've automated it. We don't even need a highly paid anchor to be able to spit out this level of basically empty financial news. But in other cases, we may actually discover that there is some real value to this problem, and I think there's actually some real value here. Now, when we talk about these workarounds, one of the things that we need to talk about for these workarounds is to what degree do we want to generalize these? Do we want to create an API? And in the group-weighted summary statistics problem, we discovered that actually generalizing that API, writing something that would solve all the different versions of problems that people might have without unnecessarily precluding some versions of this problem is actually quite difficult. There's a lot of areas of this. But for cumulative index max, it's actually quite simple. You could think that the only modality that you might see on a cumulative index max is what happens when you have the max visited multiple times. Do you take the first date of the max, or do you take the last date of the max, or do you take all of them? And in some cases, you might want to say, when was the earliest time that we saw the maximum value? When was the latest time that we saw the maximum value if we revisited that maximum value? Or what are all the times we saw that maximum value? And so this cumulative index max has a very simple modality. It's just earliest, latest, or all. And that's about all that you really need to consider in order to implement something like this. However, there is generality in terms of the underlying data structure that you're operating on. Well, if we take that into consideration and we try to implement our cumulative index max, we see the speed is not too bad. It's a little bit clumsy to use this as a consequence of my formulation. This code's a little bit clumsy. You see a little bit of ugliness around needing to drop this extra level. This is a very common thing that we see in pandas with these multi-indices. Sometimes when we do a group by on one of these levels, that level is present in the group itself, so you have to drop it so that you don't end up with these accidental duplications of these levels. But for the most part, it's straightforward, as long as we can get this speed to where we want it to be. Now, this was 0.5 seconds on 18,000 rows. What happens if we try to apply this problem to a slightly more realistic data set? Let's take the same construction of that data set, and instead of looking at just 180 days and 100 names, let's look at 10 years and 1,000 names. So we'll create a brand new data set with about 3.5 million rows. Not humongous, well within what we expect to be efficient in pandas, and let us try our Python implementation with the Python loop with the dot items with our cumulative index max. And when we do this, we see exactly why we are told, do not do a dot items, do not do a dot iteros, do not operate in pandas row by row at the Python level, because I ran this code about 5 seconds ago, it is still running. And in fact, if we take those 0.5 seconds and we multiply them times the 18,000 or so rows, and then multiply it up times the 3.5 million rows in our slightly more representative data set, we could see this is an 87-second problem. I don't think that's within the range of what we consider to be fast enough. And in fact, when I think about the speed of these operations, there's a tension. I find that when I go online and people talk about, I've written the fastest version of this or the fastest version of this, it is a very valid counterpoint to say, no, the code that we've written here is genuinely fast enough. But it's also a valid point to say, well, if your data set is growing, as many of the data sets that we work on, and they grow very quickly over time, and you can measure that the data set grows maybe super linearly over time, maybe what's fast enough today won't be fast enough tomorrow. And in fact, many of you know this is the danger of poorly implemented algorithms, specifically superlinear algorithms like n-squared algorithms, because on your testing data set, they are fast enough. But the moment it hits the real data set, that exponentiation makes it so slow that everything grinds to a halt. Well, in this particular case, you know what? I'm short on time and I'm very impatient. Trust me, 87 seconds is way too slow, and I think I can do better. And the question is, how do I do better? I want to use this as an opportunity to talk a little bit about something that we see more and more on the various platforms that we might use. That is the idea of benchmark GORE. Because between you and me, when we talk about making code faster, it is very easy for somebody to post on LinkedIn or on X or on Blue Sky or whatever platform they happen to use or whatever platform that everybody has decided we don't want to use anymore. The idea that it is meaningful and useful to say, I just rewrote function f and it is 2.2% faster. And it is a very useful thing to post if you want followers because they get lots of likes and they get lots of retweets, or whatever the equivalent is on whatever other platform that we're using. I don't know what we're using these days. I'm onto TikTok, so whatever the TikTok equivalent is. Well, you get a lot of engagement, but ultimately, I'm not certain that that's actually meaningful. And I'm not certain that we should really read too much into it, because fundamentally, when I think about benchmarking and I think about taking some code and making it faster, I think about it in terms of 3 major characteristics. 1, is this improvement durable? At the last PyData Amsterdam Fest that was held online, I gave a talk called Fast and Furious 7 something something Python performance. Because I thought we've seen a million talks on Python performance, and at the time we'd seen a million movies based on the Fast and Furious franchise. Here's yet another one that will bore you to death. In that talk, one of the things that I showed was micro-optimizations that occur at the Python level are not durable. That is to say, if you take 2 pieces of Python code and you see which one's faster, you actually measure which is faster, it is very likely that when you upgrade your Python version, the faster one and the slower one will invert. And when you upgrade your Python version again, they'll invert again. And what I discovered over the versions of Python that I had access to at the time was that in some cases, small micro-optimizations were not durable. As all of the tools that we build our code on top of, the version of Python, the version of the underlying libraries, update, the fastest version becomes the slowest version, and the slowest version becomes the fastest version. And thus, that benchmark OR is simply not useful, because what I want is either something that is fast enough, meeting to some sort of metric, or I want the fastest possible, and just knowing that I can, for example, do a map versus a, I don't know, I think the example was a map with a lambda or a map with a C function or something like that. Whatever the case is, it's not helpful for me to be able to get something to be the fastest only at one tiny narrow point in time. Additionally, I think about these in terms of the robustness. Because when you look at the benchmark OR, it's often the case that these are presented as though there's something you can learn from them. But when you really dig into them, some of these benchmarks are only applicable to exactly the code that you're looking at. They're not robust. That is to say, if I take that benchmark and the approach that is suggested in that benchmark and apply it to my actual example, I may not see the speed up that you have. And thus, good, great, you made your code faster. What does it do for me? And finally, I think about these in terms of generality. One of the tricks that you can use if you want to publish benchmark OR is you can find aspects of these problems that are of low generality. That is to say, you can specify certain details, assuming you have a data frame that doesn't have a multi-index, and it has a date-time index with date-time 64NS data types, and the data types of all of the columns are in 64s, then you can make this faster. But in many cases, as you all know, what looks so easy online ends up being very difficult for you to apply to your actual work, because there are small aspects where your problem differs from the problem they solved. You need some additional generality. You need to break the assumption that the index values are unique or that they're in sorted order, and then your benchmark is no longer applicable, and that benchmark is not actually providing you with any useful information. And so when I look at a problem like this cumulative index max, and I try and think, what am I going to do about it? Well, I don't know that I can guarantee that I can give you a particularly general answer. I can guarantee that I can give you a durable answer. I can guarantee that there are some approaches that we can take to work around deficiencies in pandas, specifically not operating at the Python level, that will be durable. As versions of pandas improve, my version will not be slower. It's just that pandas may catch up. They may add fastpads, or they may add functionality that catches up to what I can do. In terms of robustness, you'll see that different approaches that we might take may or may not have a little bit of tension around robustness. And in terms of generality, I would say that if we approach some of these optimization problems as narrowly and as shallowly and as quickly and as efficiently as we can, that is to say, we don't put a lot of effort into them, we try and write very shallow approaches on top of the existing tool, approaches that we assume will be transient, that we assume we will throw away at some point in the future, we can sometimes argue our way out of needing to actually generalize to all versions of the problem. So the first version of this that I wrote, I thought, what could be easier? I'll just take my dumb Python code and I'll use Numba. And I think Numba is actually a very valid approach, because we preserve all of the generality of the existing code that we have. We preserve, presumably, the robustness of this approach. You know, if it worked for me, it'll probably work for you. And in terms of the durability, generally what we say is if Numba didn't speed up your code, you just take off the decorator and you're no worse off than you were before. You only use it if it's faster, and therefore you are guaranteed some durability. Well, in truth, and let's make sure that I have that installed, but in truth, even if I look at the timing, this particular version spits out a million different errors, and unfortunately, let me actually switch over to my version that doesn't use my Mamba container. There we go, spits out a bunch of errors, and it's still not particularly fast. And unfortunately, one thing that I think creates a lot of tension in our use of a tool like Numba is I probably need to rewrite this Python code to be more amenable to the optimizations that Numba can see, because you can see all of these warnings that are being spit out are because Numba can't really see through the pandas data structure, can't see through the pandas series. And I'm beginning to enter territory that I'm getting a little bit uncomfortable in, because if I have to change my Python code in order to make it faster with Numba, I'm now beginning to think, well, if I remove the Numba decorator, do I end up with Python code that's worse than the original code that I wrote? And you can see where I'm beginning to risk losing durability or losing robustness of this. But if I do a little bit of work, I'll still get a million errors spit out, but I might actually be able to get Numba to speed this up just a little bit. I think in my test, this should take about 5 seconds. So you'll see that I get maybe a 20, yep, you can see I got a result from this in about 10 seconds. So I got an 8 times speed up without too much additional work. what I have found in the case of pandas is that it's actually a surprisingly useful technique to just drop down to NumPy where NumPy is available. Or hopefully, in cases where you're backing everything with arrow, to drop down to the equivalent there. Because in truth, with just a little bit of NumPy code, and slightly clever NumPy code, as you can see that's here, I can actually recover much of the speed that I lose from the slowness of operating on the row-by-row level in pandas. And I didn't really need to write that much code. You can see here I'm at 0.83 seconds, so it's about 100 times speed up, which I think is worthwhile. Going from a minute to under a second does genuinely bring some value to my life, and generally does suggest that as my data sets grow, I might have a little bit more leeway before I have to try something more exotic or more esoteric than this. Additionally, with this approach, you can see it's not that much code, so I'm not going to really invest too much time in validating it, in testing it, or in feeling bad when I have to replace it when something better comes along. Now, with this in mind, one of the other approaches that I showed in the problem related to group-weighted summary statistics is what happens when you drop down to Python. And I've discovered that if you start with NumPy, just pulling out the NumPy and D arrays and seeing if you can operate on those, you can actually get surprising speed-ups over what pandas can give you, even in some of these cases, specifically in cases where pandas just doesn't implement something. And you can do that at an implementation level that's very shallow, meaning you do it once, you slot it into your code, you put extra context manager to warn you when pandas updates, or you put a comment, or you add a task to your calendar, check pandas version 3.0 and see if they fixed this yet, and then remove it, whatever the case may be. And Python also gives you quite a bit of an approach for this. And so, in an endeavor to try and see if I could speed this up, I also implemented a version of Python here. But what you can see with the Python version is I'm beginning to lose generality. And I'm beginning to seriously lose generality because I have to assume, for example, that I'm looking at just a date times 64 NS index, which I'm not. One of the interesting things about the NumPy approach is the NumPy approach only requires that I have a greater than, less than relationship on the D type that's supported within NumPy. If I need generality, like I need a D type, like an object D type, this code will still work. It'll just drop down to the Python data model in order to assess what's larger or smaller than whatever. And I can then go into NumPy and maybe think about implementing a D type or re-encoding that data as a D type that NumPy is aware of. But the moment I drop down to Python, I start to get into trouble because when I look at this, you can see I have long, I have double, and if I really want to get even a small amount of generality here, like for example, the column may not be float 64, but may in fact be in 64 D types, I have to start duplicating this code with additional maintenance burden of having a version of this that works on doubles, a version of this that works on integers, and so forth and so on. And so where I have found that the Python approach is very beneficial is cases where you really do need to write just the dumbest possible for loop you can, like the group-weighted summary statistics example, and where the speed up is maybe 10 times or more over the pure NumPy version, which we saw in the group-weighted summary statistics. We got to about 1,000 times speed up over what you can do with a group by apply in pandas, and where you can suffer that loss of generality of basically specifying that these are longs and doubles and an index of a particular formulation, and you can write it as specific to your problem as possible. You see this a lot in the Python standard library as well. The Python standard library often struggles because sometimes parts of the standard library are way too general to solve the parts of the problem that you want. I have for many years complained about the ABC module in the standard library. It's useful if you're a core developer, but you can write a better, more specific, more useful version of it in about 10 lines using a meta class or an its subclass. And similarly, in other parts of the Python standard library, they're way too general. They solve problems that you don't necessarily have, and as a consequence, they're slower or less efficient than what you can write yourself. And finding that exact, targeted, just general enough to solve the problems I have, but not too specific, well, this is where, if you can find that and target that, I think the Python approach is a valid approach. If we actually try the timing of this Python approach, we will discover, unfortunately in this case, we don't really get much of a speed up. We might be able to eke out another 15% or 20% if we really drop down, if we really try and tear away the pandas layers and then reconstitute them. Bear in mind, we are paying for additional costs here, like the cost of performing that view operation. There's a couple of small costs that we have to pay here to pull the data out. We don't really have to pay much of a cost to put it back in. But whatever the case may be, at 15%, at 20%, I don't think the loss of generality is actually worth it. And so, what I wanted to share with you here is not to bore you to death about cumulative index max, which, trust me, is a very, very interesting problem, just as group-weighted summary statistics is. But instead, to get you to think about places where the tools that we're using really are under active development. There are places where they simply are not finished. There are places where we ourselves can contribute to fill in the gaps. Cumulative index max is a little bit more than an afternoon of somebody's work, but it would be a good starting project where somebody wanted to get involved in pandas development. And how we might think about solving these kinds of problems in terms of actually getting durable, robust, generalizable results, as opposed to just seeing something online that says, I made this 2.3% faster, downloading it, putting a lot of energy into it, and then discovering it doesn't actually do anything for you. Well, this has been Cumulative Index Max. My name is James Powell. Thank you all for joining us. I think we have time for very few questions.
Thank you. Thank you, James.